This question, sir, how this two organs are same?
Two,
What function has been done?
because it is mentioned that two identical photocathodes means frequency of incident line, not threshold frequencies. Incident frequencies are identical. That is why this F1, F2, I mean W1, W2 are same. Okay, so when the incident on the metal surface, then what is the relation between the velocity of ejected photoelectrons? Then if velocities of photoelectrons coming out are v1, v2 respectively, then hmm, then which of these relations is correct? HF1 is equal to W plus of m v1 square. HF2 is equal to W plus of m v2 square. So to find the relation between velocities, and if you see the observation, I mean options, there is no expression for work function, so that means you have to subtract this. So you have to remove work function. Then only this kind of relations will have. So for that purpose, we are subtracting them. So 1 minus 2, or 2 minus 1, anything you can take it according to the observations. I mean options. You have to simplify for the even at the end. So 1 minus 2 if you take H into F1 minus F2. H1 minus FHF2 right side. Is H is constant common. You can take it as H into F1 minus F2 is equal to here W minus W becomes 0 of M. M is constant common again. By taking this out, you can write V1 square minus V2 square here. Then you get V1 square. Uh, as per the options, you have to simplify. V1 square minus V2 square. If you keep it here and if you set this to the side, it becomes 2H by M into F1 minus F2. 2H by M into F1 minus F2 will be the correct answer. So this is okay. Okay. Next step. Okay. Yeah. Okay. Fine. Question number three, right? So the question is, the work function of a metal is 2.5 electron volt. Work function of a metal W or phi is 2.5 electron volts. The maximum kinetic energy of the photoelectrons. The maximum kinetic energy of the maximum kinetic energy of the photoelectrons emitted if the radiation of wavelength the radiation of wavelength 3000 angstrom units 3000 angstrom units falls on it is what? So what is maximum kinetic energy of photoelectrons emitted? Given h and the c values are given. H, that is Planck's constant, h is equal to 6.63 into 10 to the power minus 34 joule second, and c, speed of light, is given as 3 into 10 to the power 3 into 10 to the power 8 meters per second. So what is the kinetic energy of the emitted electrons? We are asked to find. So what you can do is on the maximum kinetic energy, you have to just make use of the Einstein's photoelectric equation. From Einstein's photoelectric equation, from Einstein's photoelectric photoelectric equation. That is here incident wavelength of incident light is given. So in terms of lambda, I can write it as that c by lambda is equal to work function plus kinetic energy or maximum kinetic energy. So you're asked to find this. So this further you can write it as Ke max. Ke max or maximum kinetic energy of visited photoelectrons is equal to hc by lambda minus w. Here work function of the metal is given in electron volt and lambda is given in angstrom units. So this is given in electron volts. If you substitute this in angstrom units, this SI units, you will get this part of the energy as joule you will get. So to get this part also in electron volts, you have to take this as a shortcut. What is that is? This implies Ke maximum is equal to hc by lambda. I can write it as 1 second. You can express it as 12,000 12,400 by lambda. If you take this value in angstroms, then you will get this energy in electron volts. In electron volts minus W in electron volts. If you take, then you can take the difference. Okay. So this you can take it as 12,000 12,400 and lambda. What is the value of lambda? 3,000 angstrom units. So this value in electron volts minus W is 2.5 electron volts is also given in electron volts, right? So if you simplify this, two zeros gets cancelled. This 124 by 30 you can write it as 12.4. You send this 12.4 by 3 will be good. Then you simplify further, you'll get 4.13 in electron volts minus 2.5 in electron volts. So on simplifying this, you'll get 4.13 minus 2.5. 4.13 minus 2.5. So 0. Then what is this 11 6? 3 here, right? 3. So this is 6. This is 1.63 here. 1.63. 1.63 or 1.6. electron volts will get. But if you say the options will be given in joule. So to convert this into joule, so you can write Ke max is equal to 1.63 electron volts. To convert this into joules, you have to write it as 1.63. The 1 electron volt is equal to 1.6 into 10 power minus 19 joule. So this approximately, if you take it as 1.6 only, then 1.6 into 1.6 is 2.56. 2.56 into 10 to the power minus 19 joule. So this is the option. So you get 2.56. They have given some around some 2.6. So 2.56 you can also forward it as 2.6. So approximately you can also make it as depending on options. This equations and all you have to. K max is equal to 2.6 into 10 to the power minus 19 joule.
So for all this, it must be taken
So depending on, so here because valid work function is given in electron volts. So in some subtraction, so every term should be in same units. So because it is in electron volts, you have to take this also in electron volts. Otherwise, you convert this into joule, then you can take SI values of this. You will get joule only here. Then final answer automatically will be joule. Otherwise, you do the final answer, you take it in electron volts, then convert it to joule. This way, either way. Accurate measurements of atomic masses is carried out with mass spectrometry, the device which is used to measure the accurate mass in atomic mass level. The atomic name is not in kilograms. So of course you can go that in kilograms also by using this, but accurate measurements of atomic masses is carried out by using mass spectrometry. Okay, the measurement of atomic masses reveals the existence of different types of atoms of the same element. Of the same element. What does it mean? The measurement of atomic masses reveals the existence of different types of atoms of same element. Same element, say for example, carbon. Carbon element is same. And this what you call specified measurement has revealed that, and what it has revealed, the measurement of atomic masses reveals the existence of different types of atoms. Different types of atoms are all we can also call as different types of nuclei. So, so that means the carbon can have say 6, 12 we will have, but if the atomic mass is different, so not only 12, some different mass atomic mass also will getting for carbon like C13 also will get, but 6 will be same. Atomic number will be same, mass number will be different. So based on these different masses we are getting, it was revealed that same element is carbon only, it can have different masses. So different atoms, different nuclei, same element can have different nuclei with the different masses. So based on this, they have classified in different types, like isomers, isomers, classification as carried out. So that is what they have mentioned. So the measurement of atomic masses reveals the existence of different types of atoms of the same element, which exhibit the which exhibit the same chemical properties but differing in mass. Such atomic species of the same element differing in mass are called isomers. Based on this observation, they are classified. atoms are
Same
classified
element, different mass, right?
different same element, but different masses they are having. So same element, different atoms are having different masses. So such atom means every atom will have nuclei. So we use the name type of nuclei instead of using the name type of atoms. So these kind of atoms which are having different masses, types of atoms. Here one can underline the atoms are nuclei. Types of atoms are nuclei having different masses are called isotopes. Such atomic species of the same element differing in mass are called isotopes. So the origin of that, how it was got is we put it over here. Okay. So it was also found that practically every element consists of a mixture of several isotopes. Practically, in reality, every element, every element,
So,
every element consists of a mixture of several isotopes. So that means some elements may have three isotopes, some may have four isotopes. Mixture of isotopes is an element. So there, one isotope can have different abundances. So
so that one I know. Later,
relative abundance is something like we come across. So that is, say for example, so here, say like say for example, simple example let's consider hydrogen H11, H12, H13 will consider. These are isotopes of
hydrogen.
hydrogen. You can call it as hydrogen or protium also can call it as. This is deuterium, this is tritium. Protium, deuterium, and tritium. So here, in all of these atoms, atomic number is same, mass numbers are different. So this all together will give you hydrogen. Okay, so this different all mixture of these isotopes gives you the actual element. So in that, this part can have this may have 10% of this isotope, and it can have some what you call eight. Say for example, I'm telling. For example, this may have some eh, uh, 80 80% of this isotope, but this abundance of this may have 10%, but some of this will give you 100%. So that will give you the actual hydrogen element.
So this
Likewise,
is called as relative
the
abundance.
relative abundance. Based on this, when some numericals there, when you use in general form also it is. Similarly, if you say carbon, physics 12, physics 13, physics 14, something like if you say 6, 14. So if it is said to be having three isotopes, some may have only two isotopes, some may have three isotopes like this, some may have four isotopes also, right? Like this kind of elements if you consider. But if you have only some two isotopes, one isotope can have some 60% of abundance, some can 40% of abundance. So a mixture of these two will be equal to 100%. Like 100% of the element will be the result of the mixture of these isotopes. So like this abundance, different abundances, these isotopes will carry. And about this we'll discuss with you some examples. Right? So what they have given here overall, it was found practically every element consists of mixture of several isotopes. The relative abundance of different isotopes differ from element to element. That's what, from element to element. Chlorine, for example, has two isotopes having masses 34.98 atomic mass units and 36.98 atomic mass units, which are nearly integral multiples of mass of hydrogen atom. Okay. The relative abundances of these isotopes are 75.4 and 26.4% respectively. This what do you call the first isotope is said to be having 75.4% of the total. Okay, the total mass you can say. Whereas this isotope, the isotope which is having this mass number is said to be having 24.6% of the total. Okay, so respectively, thus the average mass of chlorine atom is obtained by the weighted average of the masses of the two isotopes, which works out to be like this. So how can you take this? So this is general by using the general relation. We will get this one. What do you call? We use one relation like then one in what is it abundance, the fraction of that you can say, the fraction of that isotope into mass of that isotope plus the fraction of the second isotope into mass of that isotope divided by. Okay. Yeah. So just consider this as n1 percent is the total abundance. You can take it as in 100 parts we will compare this one. Okay. If in one part if you want to compare this, we will take it as fractions. Otherwise, in percentages. Yes. Okay. So this will give you what you call atomic mass. Usually, the atomic mass is in the general expression if you see x z a always will be integer. But sometimes you'll come across it for say for example like for fluorine 25.47 atomic mass it will get instead of discussing integral. So why that decimal comes? That is because of this abundant process. Okay.